welcome back. We are in section 5.4, looking at interpretations of the definite integral. So we've looked at the definite integral as a concept, as an area under a curve, right, between the curve and the x-axis, between two curves, and now we're going to start interpreting in different contexts. So oftentimes when we talk about the definite integral, this area under the curve, we're looking at total change of a quantity. So we say if f of t is a rate of change, okay, so f of t is a rate of change of a quantity, then the integral from a to b of f of t dt is the total change in quantity between t equals a and t equals b. Okay, so if we have the function is a rate of change and we find the area under that curve, right, that integral, then the integral is going to give us the total change in quantity. So how much did it change at that growth rate? Okay, so first up, let C of t represent the cost per day to heat your home in dollars per day, where t equals 0 represents January 1st, 2019. Interpret the integral from 0 to 90 of C of t dt. Okay, so let's look at the function C of t. So C of t represents cost per day. Okay, so the units on this, the units on C of t are dollars per day. So the units on, let me go ahead and handwrite this. The units on the integral from 0 to 90 of C of t dt so the units on the integral, if C of t represents the rate of change, right, it's cost per day, so how much the cost changes per day to heat your home, the units on the integral are dollars. Because remember that integral represents total change, so it's just how much change is there in the amount of money. So the integral represents the total cost to heat your home for the first 90 days of 2019. Okay, so if the function C of t tells us the cost per day, then if we look at the area under that curve for the whole 90 days, that area is going to give us the total cost of heating the home for those 90 days. Okay, so the function was a rate of change, so the integral gives us the total change in that quantity. All right. So next up, a bacteria colony initially has a population of 14 million bacteria. Suppose that t hours later, the population is growing at a rate of 2 to the t million bacteria per hour. First up, give a definite integral that represents the total change in the bacteria population during the time from t equals 0 to t equals 2, and then find the population at time 2. All right, so part A. So for the integral, we want total change from 0 to 2, right? So over the first 2 hours. So that's integral from 0 to 2 of the function, right? 2 to the t dt. And that's it. So that's our integral for this scenario. And then for part B, Then finding the population at time t equals 2. So using technology, we can get the value of the integral. So the integral from 0 to 2 of 2 to the t dt is approximately 4.328. Okay, so that's the value of the integral. But the value of the integral just tells us total change. It tells us how much the population of bacteria has changed from 0 to 2. But the population, if you remember, started off initially with 14 million bacteria in it. Okay, so population, actually let me type this. So the population was initially 14 million and then increased by 4.328 million. Thus, after 2 hours, the population is 14 plus 4.328, so that's 18.328 million bacteria. Alright, so again, the integral giving us that total change, right? How much it increased or decreased from 0 to 2 hours. Okay. So let's look at another example, this time incorporating that graphical interpretation here. So a man starts 50 miles away from his home and takes a trip in his car. He moves on a straight line and his home lies on this line. His velocity is given in the graph. So this graph here, this is the v of t. Oops. So this is his velocity graph. Okay, and this is our time here. So the questions: when is the man closest to home? Approximately how far away is he? When is the man farthest from home, and how far away is he then? And then what is the total distance the man has driven, and what is his net change in distance? Okay. So first, before we answer these questions, I want to look at what's really happening here in this scenario. So a man starts 50 miles away from his home, and he's moving towards his home and then away from his home. So on this graph, notice what's happening. As he starts here at 0, the man has positive velocity from here to here. Does everybody see that? Right? This curve is positive between 0 and 2. And then from here to here, the curve is in the negatives, right? Which means the velocity is negative. So what's really going on is the man, so let me write this down. So note, okay, so what's really happening here is the velocity increases then it hits 0, right, at that point at 2 where the function is crossing the t-axis, then is negative. So what does that mean for his driving? Well, that means he is driving forward. And when we say forward, that just means closer to home. Then when his velocity hits 0, he stops. And he turns around. Because negative velocity means he's going backwards, if you will, or just the opposite direction from home. He's going away from home. Okay, so then he turns around. Okay. I don't know why this doesn't want me to type velocity. There we go. Okay, so velocity is positive, and then it hits 0, which means he stops, and then he turns around after that and is heading in the negative direction. Okay, so when is he closest to home? Well, if he started off here at 0 and he's been driving closer and closer to home this whole time, right, going forward, forward, forward until 2, then he stops and turns around. Well, this whole time that he's driving away, he's getting further away from home, right? So we don't want any of those times. All we want is this time right here, right, where he's actually driving closer to home. He's driving forward, okay? So what that means is the closest he is going to be to home looks like it's going to be here at 2, right, after 2 hours. So that's going to be 2 hours. So let me put this in here. So part A. So the distance he travels during the first 2 hours closer to home. We can compute that distance approximately by finding the area under the curve. Okay, so we're going to approximate the area under the curve. Closer to home is the area under the curve. Under the curve from t equals 0 to t equals 2. There we go. Alright, so we're going to need to approximate this area. So this area is approximately, we'll come back to that in a second. Okay, so when we're interpreting this graph, at this point, really we just need to look at the grid. Okay, without a grid this would be a lot harder. But you could do a rectangular approximation on this, but we're just going to kind of eyeball it from the grid here. So let me thicken this a bit. So just want you to take note, every one of these larger grid boxes here. Does everybody see those grid boxes? Each one of these has a height of 10 and a width of 0.5 or 1/2. Okay, so that means the area in here, the area of each one of those boxes is 5. Okay, so let's look at how many of these grid boxes we can see in here. So from 0 to 2, so full grid boxes, I've got 1, 2, 3, 4 full ones. And then if we start looking at the pieces, kind of try to piece these together. So I would say, let me get the pen in here. I would say it looks like this part and this part, if you combine them together, would make about 1. Again, this is just approximate. And then, right, this one, and maybe this one would make 1. And then looks like we have the makings of about 1 more up here. So we're talking 1, 2, 3, 4, 5, 6, about 7 grid boxes going on here. So if we have 7 grid boxes, then that means 7 times 5, right? That's 35. So that's 7 times 5. That's our third area of 35 underneath this curve. So this area is approximately 35 miles. So, to answer the question, he is closest to home after 2 hours. And what is his distance away from home? Now be careful when answering this, because the first inclination would be to say 35, because the area is 35. But remember, he started away from home, and he's going towards home. How far away was he from home? Go back and look in the problem. So if you go back, he started away 50 miles away from his home, and now he's gone 35 miles closer to home. So at this moment now, he is 50 minus 35, which is 15 miles from home. Right? So after the first 2 hours, he's been driving closer and closer to home. He's now 15 miles away from his home. But at that point, then, he stops and he turns around. I don't know, maybe he was at work or something and he forgot something in the office. So he stopped, he turned around, and now he's heading away from home. So when is he farthest from home? Well, we can compare because we know that initially he started off being 50 miles away from his home. So that's certainly far away, but if you look at this area here, he's heading away from home, and this area, he's going very far away from home. So it looks like he's actually going further than he was before. So from 2 to 5 here, 2 to 5, whatever the units are on this, hours, minutes, whatever it may be, he is driving further and further away from home. So it looks like he's going to be furthest away as we get even further away towards the end here. So let's look at this. Okay, so here we go. So part B. Alright, so from t equals 2 to t equals 5, he moves away from his home. This area is approximately, let's take a look. So again, this one's a little bit bigger, so we've got some more work to do on this, but we can look at the boxes again. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 whole boxes here. So that's already putting us at 75. And then we've got kind of the fractions of all these little pieces here to take care of. So you can go in and try to approximate, and you might get a value that's slightly different than what I get. And that's okay because this is truly just approximation. But if you count up and round those boxes, I got that it's approximately 105. Okay, so I got about 21 grid boxes in total. So this is approximately 105 miles. So now this doesn't mean that he was 105 miles away from home, because at t equals 2, right? Because remember, he started off at 50 miles from home. He drove 35 miles towards home, stopped, so now he's 15 miles from home. Turned around, and now he drove another 105 miles away from home. So he was already 15 miles from home, at time t equals 2. So he is farthest from home after 5 hours. He is 105 plus the 15 he already was, so he is 120 miles away. So he's furthest from home after 5 hours, and he's 120 miles away from his home. Okay. So now part C. So part C is kind of interesting. This is where we start to look at kind of these areas again a little more differently. So what is the total distance the man has driven, and what is his net change in distance? Okay. So these are asking for two different things here, but both of which we need to try to be comfortable with. So first it's asking the total distance he has traveled. So the total distance, so the total distance he has traveled is, that's going to be, so he started off 50 miles away from home, but he drove 35 miles towards home, plus then he drove 105 miles away from home. So that's going to be 140 miles. So this would be like if you're looking at the mileage on your car, the car doesn't care which direction he was driving, right? It just matters that you were putting miles on the car, using up gas. So the odometer would read 140 miles, right? The trip meter would say he's gone 140 miles total. But then when we're asking about the net change in distance, so his net change in distance, so this net change is asking us how far away is he from where he started. Okay, how far away is he from where he started? Okay, so let's see. From where he started, he drove 35 miles towards home, so 35 miles forward, but then he turned around and drove 105 miles backwards. So that, if we compute it, that's going to be negative 80 miles. And if you're thinking, wait a second, why is the distance negative? Because it's a net change. So we're looking, think of it as he's 80 miles behind where he was when he started. Okay, so because velocity can be positive or negative, so the net change in distance can be positive or negative. When we're computing integrals, we are often looking at net change. Okay, integrals give us net change because in the first calculation, the total distance traveled, it only cared about the geometric side, right? It's positive area, positive area. Doesn't matter what direction it's going, it's 35 plus 105. But the net change takes the fact that this area is positive and this area is negative into account. And it asks us to then add the positive area and subtract the negative area, just like when we looked at integrals in the last section. Okay, so when we're looking at integrals in terms of distance and interpreting them like that, we're going to be seeing the integral giving us net change, and then the total distance traveled being just basically the absolute value, basically taking all the negatives and making them positive, so we can see total distance traveled. Okay. So when we come back in section 5.5, we're going to be looking at more application of the definite